Last time, we introduced the notion of a local condition for deformation ring. So let me sort of first recall the setup. I have this roll bar and residual Galois representation. A residual representation. And from this, I get a R row bar frame. This is a deformation ring. And I will have slope. And this carries an action of PGLN hat. A local condition is a PGLN stable. So last time I discussed two versions of stability under the action of this PGLN. One is sort of scheme theoretical, the other one is pointwise. At this moment, I assume this is scheme theoretical. Ideal I of R row bar frame. So last time I did an example. Let me maybe quickly recall this, and then I'll kind of discuss, quickly move on to a different description of this. So suppose I have a residual Galois of the Galois group QP, and this goes to GL to F, and the Frobenius P goes to 1 and P. Okay? And this one has a universal deformation ring. So this is unrarified extension, and then we computed last time the universal deformation ring. So this takes the following form: X, Y, S, T, and B. Functional by a relation B times T minus PS. Such that for the universal representation of the Frobenius, it looks like 1, Y, 1, 1. So it's a sort of conjugate of this. Conjugate of a diagonal matrix, where this 1, X, and Y, 1s are the eigenvectors. And over here, I have 1 plus S and then P plus T. And for a time generator tau, the action goes as follows. B. Okay. So that's what the action is. Last time we talked about this deformation ring has two irreducible components because I'm quotient by a sort of product of two equations. So last time we discussed how if we write split of this R row bar frame, it has two components. So let me call this one split of R row bar unramified. This is split of where quotient by B, namely where B is 0. So if B is 0, the initial group will act straight away. Similarly, let's say the other pieces are row bar frame, frame. I call it Steinberg. This is split of R row bar frame over the other equation T minus PS. In the sense that over this component, the two forbidden eigenvalues, the ratio of the two eigenvalues is P. Right. So let me make a remark of. So we do, okay, when we write formal schemes, I'm looking at sort of an integral structure. But later on, we're going to talk about sort of generic fiber. So if we look at what the generic fiber of this looks like, namely I invert L on the deformation space, and then I take a spec of this, and this really just takes sort of all possible QR bar points. So what do I get here? I get that, well, let me maybe write this as a union of the other two, because I guess as schemes, it's, the deformation rate is a union of the two components. So let's write the other two as a union of the unramified part and the Steinberg. Okay, and then for the unramified part, what we're seeing here is that you're quoting out the equation, the variable b there. So now you're left with x, y, st. So that means that this is just a set of elements st, x, y, st in QL bar for 4 elements here. But then you wanna evaluate these x, y's in the big variables, the capital letter variables, so that the power series converges. So therefore, what you require is that the absolute value of these things are all strictly less than 1. Okay? So in other words, at least this component is a polydisk. Actually, same for the other one. Over here, you are quotienting for the Steinberg component, you're quoting out the idea of T equals PS. That means that you're enforcing T being PS. So therefore, you can forget about the T variable, and then B can go freely. So you have S and B. And that is QL bar 4, and that's still the same condition. Okay, so therefore, this deformation space is sort of a 2 4-dimensional polydisk intersect together. Over the locus, I guess, where on this disk you used to see where B equals 0. And on this disk is where S equals P times T. So in other words, they intersect. So this is a 2 4-dimensional polydisk. They intersect as a 3-dimensional polydisk. So that's basically what roughly this looks like. So geometrically. So in the sense that integral structure is very useful for a lot of deformations. Whereas if you look at sort of generic fiber, it's more visualizable in some sense. So later on, towards the end of this, I guess later today's lecture, we're going to see that we're going to try to sort of understand the generic fiber of such local differential space, and that will give us, so over there the structure is a little bit better. I guess on the special fiber there might be singularities, and on the generic fiber it's usually smooth. Okay, so let's come back to discussion of local differential. But in practice, if you think about it, this is not very helpful in some sense. Somehow it relies on computing the entire deformation space. And somehow in general it's really difficult to say which ideal is PLN stable. Of course, over there, you can take, okay, the ideal defining one of the irreducible component, or you can take the ideal defining the other irreducible component, or you can take the intersection. But in practice, sometimes we have to take smaller ideals. It's really difficult to tell which ideal is stable under this PGL in action. And also, usually it's not very easy to write down what the ideal looks like. So instead, we describe what type of representations you see after you're quotient out by the ideal. Namely, for example, you say, okay, on this component, all the representations are ramified. On this component, all the sort of the 2 ideal values of the Frobenius have ratio P. So that's kind of a condition we want to impose. But there's a problem. It's not like you want to, I guess, get a theory to say that what kind of condition you impose as some sort of condition on this deformation problem, so that it does result from some sort of ideal there. So this is the definition of, this is the following definition. The name follows from a paper by Closell, Harrison, Taylor. I guess it's just carried over from there. So it's called a deformation problem, called D, is a collection A row where A is a complete Euclidean local O algebra and rho is a lift. In the sense that I'm collecting all allowed deformations. I guess, for example, in an early example, you could take D iramified. As in that example, it's all the sort of the A and the rho, where I guess, for example, rho belongs to this usual deformation ring. This is the usual deformation, but yet I want a rho to be iramified. Right? So that's a typical example of a deformation problem. Or you can take Steinberg, which is replaced here by Steinberg, in the sense that the two forbidden eigenvalues have ratio p. Okay. So this is an example of what we're going to do. What type of sort of condition we can put out so that it does result from a PDL stable ideal? The following condition. So a differential problem D is a collection satisfying the following conditions. First of all, you're going to have the rho bar in it. The rho bar is allowed. Secondly, if you have a morphism in C and L O, in this complete local, in this category you have a morphism, then if one of the, if A rho is allowed, I guess allowed deformation, then you can compose it together. Get sort of allowed deformation like so. In the sense that, okay, your rho is from gamma to GL and A, right? And then you can compose it with F. So the composition here, F composed with rho, is allowed. So in other words, alternatively, one can reinterpret this condition as you can maybe define this deformation functor, definitely this, is to be all the rows such that A rho belongs to D. Okay? So that's another way to talk about deformation problem. And this is the subfunctor, so a subset of the deformation rho bar frame. And what the second condition says is that this is a subfunctor. Not just sort of subset, but rather a sort of subfunctor in the sense that, i.e., for whenever you have a morphism in this category of complete Euclidean local O algebras, then of course we know that we have a, this will induce a morphism between the set of a map between the set of deformation to A and deformation to B. And the second condition here I wrote down says that it's called subfunctor. So that we have two subsets of these two. And then it takes, I guess it sort of takes this subset to the center. But that's what the second condition says. Thirdly, suppose that F from A to B is injected. In this category, then this A rho is sort of allowed even if B, F circle rho is allowed. By 2, if A rho is in D, if rho is in, then this is in D. So if this map is injected, then you can have the converse. The first condition, I guess, is the most important condition. It says that suppose that I have two rings. if I have two complete Noetherian local O algebra, I have two ideals, I1 and I2. A1 and I2 in A2. So suppose that there's an isomorphism after you quotient by these two ideals. So suppose you have two rings and you have two ideals, and suppose you quotient now by these, you get an isomorphism, and of course I want f of rho 1 mod I1 being rho 2 mod I2. So basically these two representations are sort of same after modulo the corresponding ideal as well. Then from this I can form a bigger ring by sort of putting A1 and A2 together. Then I do A1 cross A2 over A1 I1. So what this is a ring. What this ring is that you're taking the elements A1, A2 in A1 cross A2 such that I guess f of A1 mod I1 being A2 mod I2. So you can check this as a ring. And then over this ring you can sort of direct sum the two representations. And just sort of put together this rho 1 and rho 2 together. This is sort of allowed by this differential problem. Okay. And now continue on the next property. If I1, I2 is a nested sequence of ideals of an object A in complete local algebra, such that intersection of all I is 0. So I have some sort of decreasing sequence of ideals that converge to 0. And if A rho lifts rho bar such that we know that if I A modulo, so maybe how should I do this? So if I modulo each of the I here, the ideal, this is allowed in our deformation problem. Then A rho is allowed in our deformation problem. Last one. So this is some sort of condition that allows you to take limit. Last way, if I have a sort of allowable condition and I have an element A in complete, A is in the sort of possible conjugates, way to conjugate things. So that means this belongs to the matrix. And so then basically this A and conjugation of this representation belongs. So this will correspond to the PTL and stability condition we imposed earlier. Okay, so theorem is that this way of describing local deformation problems or local conditions is the same thing as what we had before. So there's a bijection Let me write it more so precisely. Scheme theoretic PGR unstable ideals I of this deformation ring is in one-to-one correspondence to the deformation problem. D for this representation. As we defined over there. So usually the notation is denoted by I goes to, I guess, DI, and D, just a notation, goes to I of D, okay? And right, maybe as a remark, to talk about the relation with your pointwise stability, is that if the corresponding ideal we're talking about is radical, namely I equals to square like right of I, so whatever I describe here is the same thing as pointwise. So, or maybe I just write it PGLN hat deformation ring stable ideals Y. In the sense that somehow, if an ideal is radical, then scheme theoretical stability is the same thing as stability under the sort of points. So let me explain how this is proved. Rather somehow the proof is morally somehow constructing a map going this way and going the other way. And then it's not that difficult to see that, I guess, the two maps compose two identity. So let's give the construction one way. So maybe I just define it over here. So let's start with an ideal I. I'm going to define the corresponding deformation problem as we define over these, setting these properties. So let's see. So this is basically consists of all the A and rho such that, of course, A is a complete Noetherian local algebra, and rho is a representation, of course, lifting rho bar. And then if I have a representation lifting rho bar, this by universal property of the deformation ring, I would get a natural map from R rho bar frame to this A. Let me call it F rho here. Right? So if I have a representation lifting rho bar, then I would have a move from the universal deformation ring to A, and I wanted to factor through the quotient by I. In the sense that I'm taking only the subsets of those rows that factor through here. And let's verify these conditions. Let me think, what do I want? Let me go up here. I want to leave out R. So let's verify some conditions. I'm going to do all the conditions. I'll just maybe do several interesting ones. So let's check. For example, 4. Condition 4. So suppose I have two rings and two ideals of these. And suppose that I have an isomorphism between the ring modulo that I corresponding ideal and such that the corresponding lifts rho I and rho 1 and rho 2 are sort of identical modulo these ideals. Then I can form a sort of product ring and this representation. You can kind of glue this representation together. So what's going on here? So let's see. So the condition says that, oh, my bad. supposed to have this ideal that suppose that isomorphism, which is the ideal. Sorry, I missed a condition. Suppose that A1 row 1 and A2 row 2 belongs to this condition. Then you can glue them together to the next condition. I apologize for that. So, okay, because A1 row 1 belongs to this condition, and my condition defined as the corresponding homomorphism factor through I. So maybe I can write things as follows. So I have a homomorphism going to A1. This is essentially F row 1 will give me. And I have another one going to A2. That's what F row 2 will give me. Right? And then I have isomorphism between these A1 and A2. So that means that maybe so my F will get an isomorphism between A1 mod I1 and A2 mod I2. And the condition that F row 1 mod I1 is equal to row 2 mod I2 means that if I compose my map from the universal deformation ring all the way to here, that would be the same thing as composing it all the way to here after I identify A1 mod I1 and A2 mod I2 via F. So that means this is a commutative diagram here. And then this is actually somehow the push. You can think of it as kind of the this is sort of the pullback of this ring homomorphism. So once you have this diagram, you see that how should I put this? So I put this product ring in the middle. But I don't have much space to write it. So I have this product ring in the middle. Right, it will map to here and map to here and being identical over here. So this is kind of the Cartesian pullback of this ring home. And then because the whole diagram commutes, then there's a natural map from this one, because this already maps this to make it commute. So you have this natural map from this to here. And therefore, and this basically corresponds to the direct sum of two representations on this ring. Well, that's what. So how you check for it. Okay? So check 6. Let's do 6. 6 says that, okay, how about representation in here? And the element in this possible conjugation, then this is also served in the local condition. Okay? But I'm going to erase this because I don't have space. I want to write proof of this here. So what do I have here? So this, just give you several typical examples of how to do this. So I have a row in D. What that means is I have the associated F row. Whenever I have a lift of row bar, I have a map from the universal deformation ring to A, and this will factor through this R frame I. Okay? But then what about the conjugates? Right? When you have conjugates, you get another map from the frame deformation to A. But then how do you construct the options we can reconstruct? Maybe. F A row A inverse as follows. The point is that the frame this can be constructed as follows. You start with the deformation ring, and then you apply acts. Because the PGL and action last time I actually kind of did this diagram. The PGL, so act goes as from PGL and act times spuff of R row bar frame to spuff of R row bar frame. Okay, so this is the group action. And then if you think about it in terms of rings, that's what you get here. And what about this sort of A row inverse row? Over here, the element A will give you a homomorphism from from R row bar to A. So that's called A star. Excuse me, not what I'm saying. Sorry. I mean the A. Let me write it this way. So A belongs to PGLN hat A, right? By that I mean I have a stuff of A mapping into PGLN as a scheme. So that's what I mean by an A point of this. Turning the other way, I will get an A star from this to A, the ring A. On the other hand, this side, I have an F row mapping to A. So I have to take the product, get to A. So this is my F A row A index. Okay? And then why does it factor through the ideal I? Well, let's see where the image of I lands. So the ideal I is ideal here. And the condition for scheme theoretical stability is that the pullback of this I is basically contained in, I guess, O of PGL and hat. We cancel with I here. Right? Now I want to see where this have after this step. But note that this F will map this to 0. This part to 0. And this I can map to anywhere, I don't care. But this is going to be mapped to 0, and therefore we continue to be 0 down here. So that means if I go down this way, it's going to be get to 0. And therefore this will factor through quotient by I. And therefore we prove that if A row belongs to D, then the conjugation of row by some element A will still belong to D. For the D, I defined over there. So again, those are somehow the two most important things about this direction. So now let's maybe talk briefly about the other direction. Let's see. Let me pull this down. So suppose, on the other hand, I have a deformation problem satisfying all these conditions. So suppose, conversely, given I think it's called deformation problem. D. I can define, I'm going to construct ID, the ideal corresponding to this deformation problem. So what I want to do is I want to define the following collection of ideals. I'm going to call it J or I. It's a fancy letter. I'm taking all possible ideals, I. Such that if I take the universal sort of deformation ring quotientized as ideal, and then take the universal deformation or the universal representation, and then mod I. So this is a ring, and this is a lift of row bar on this ring. So this belongs to. If it belongs to B, I put the ideal in this collection of ideals. And this is not empty by 1. The one I already erased. Namely, I take the maximum ideal, the quotient is F, and this is row bar. Of course, it's not empty. Basically, the goal is to we'll take the ID to be the minimum number, member in this collection. Okay, and therefore, somehow we have to make sense of what I mean by the minimum number. So here's a claim. There are a couple. These conditions are used to show that they have a minimum number. So let me check. For example, probably most importantly, check the following condition that the collection is closed under a finite intersection. Or rather, I'm going to check it closed under intersecting two ideals. Okay, say that I have two ideals. Okay, in this collection, then, of course, I know that R rho bar frame over I1, and I take the universal representation mod I1 and mod I2, so universal mod I2 belongs to B. Okay. Now I want to glue it. I want to know whether intersection of these two rings, intersection of these two ideals, if I quote out the universal ring by that, whether that corresponding thing belongs to D or not. So here's a simple nonlinear, so abstract algebra statement. So if I take the intersection, rather maybe put it this way. I have these two rings. I can map it sort of together to the sum of two ideals. So this one maps to here, this one maps to here. You add them up, and the kernel is precisely R rho bar frame divided, quotient out by I1 intersect with I2. So this is an exact exercise to check that. Thus, I can rewrite this as the so-called fiber product we had earlier. Not fiber, but sort of, not tensor product, but sort of this sort of naive product. As such. And therefore I can, I already erased that over here. So now I can use 4 to conclude. Because you see that I have so this is going to be my A1. Different color. So this is my A1, and this is my A2. And for the ideal I1 there is actually sort of so the ideal I1 over there is maybe I1 prime is I1 plus I2 over I1. And I2 prime is I1 plus I2 over I2 of this ring here. And then I can glue these two representations over to this bigger ring, which is precisely the universal determinant quotient by the intersection of the two ideals. Right. And then, of course, gluing the representation and so. So therefore, by 4 would be good. Namely, the intersection will belong to this collection of ideals. So that's roughly, I didn't check all other properties. For example, you have to check that it's not only just closed under finite intersection, you have to show it is closed under infinite intersections. So that's where the condition 5 already erased. Anyhow, so after all these, somehow we show that I can already erase the statement. Oh, no, right here. Right. So the scheme theory of PDL unstable ideals I will correspond to the usual deformation problem, satisfying the 6 properties. So in general, whenever later on I want to specify what type of deformations, for example, especially when L equals P, I can say, okay, I want to deform my things into some sort of crystalline representations or deform it to some sort of semi-stable deformations. I can check for the condition on the right-hand side without knowing what I is. So it's some sort of it's some sort of abstract way of defining a deformation. Okay, so I leave it as an exercise for you to fill out, putting all the details of proof. So now maybe let me give an application of why let me discuss somehow how this fits into the picture of global deformation rate. and how this sort of local condition comes into the picture. So, you're right. Global deformation. Ring with local conditions. So let's fix things as before. F is a number field. And F a finite set of places. Including those B dividing L infinity. And key is where we're going to put frames, which is subset. And also want L to be not divided N, so that we fix the determinant of our deformation. In fact, we typically require T to contain all the places dividing L infinity as well, but what we're going to do now, anyways, doesn't quite require that in this generality yet. We can assume that when we state the main theorem. So let's say I have a residual Galois notation. An absolutely irreducible representation. And I take chi, the character, lifting the determinant. And at each of the places I put frame, I specify a local condition. Local deformation problem, I guess. Call it dB. For the restriction of your global residual Galois condition. Then I want to define the following. Function. Let's call it def of row bar frame of global D, where D is some sort of collection of all the dBs. So this, as usual, it's a function on the complete Noetherian local O algebras, sending an A to the following data. So send it to rho and, as before, HB for HB and T. Where rho is a sort of continuous lifts of rho bar. Continuous representation. Lifting rho bar. And the determinant of rho is my given chi. Okay? And next, I want my local, maybe just write HB belongs to PGL and A, as before, for every V T. And also, I want my deformation to satisfy the local deformation problem. So rho restricted to G at D. This belongs to dB for every. And this is quoted by the usual equivalence relation when we define these properties with local frames. Oh, okay, sorry. Put the frame here with a T here. Oh, T. With a local frame, namely the action of PGLN is by conjugation on rho and right multiplication by the inverse on HB. Let me also point out that over here I read this, but supposedly I should be written sort of A of sort of conjugating by HB. Rho restricted GF HB. I suppose that should be written as this for in D. But these two are equal because of the property of the local deformation. to talk about the global to local things. So in fact, I'm just going to then this function is represented by a ring. And we have a Cartesian diagram. Actually, I forgot one thing. Maybe. Sorry, let me say that. Let me add one thing before that. So remember that, in fact, when we define local deformation problems, I defined this thing. This is all the rows of this deformation function. So this is all the rows such that a row belongs to the local deformation function. Right? And this is a function on complete Noetherian local all algebras. This is represented by R rho of our frame over this I, precisely the ideal I, or rather maybe I here. So now coming back to the global situation, and the global deformation problem is also represented by some ring. And this ring can be, well, you can say, okay, quantify by the ideals, sure. But maybe let's do it this way. So maybe write it from the right-hand side. So I have the usual deformation problem with frames at T. This maps to product local deformation problems. So, right? We talk a lot about this vertical maps, properties, set of generators, and then how to make it nice, and this patching argument. And sorry, without the condition, right. And with the condition D, I'm cutting out a closed subscript inside of this. Similarly, locally, I have this thing as well, but with a local condition dV. And this ring is nothing but R rho bar V frame. Frame modulo the ideal. Finding this deformation problem. Okay? And of course, this will map down here because if I have a global deformation, satisfying this corresponding local condition, it will map somehow. But you need to probably this ring will map down here. And this is Cartesian. So namely, I can somehow take this as a definition in the sense of this ring is basically the tensor product of the usual frame deformation ring with the local condition deformation ring over the frame and local deformation ring. Right. Let me state a key corollary of this. The key corollary of this is so fixed notation above. I have some sort of chi there, and then I want to set just like how we. If we want to understand, we understood somehow the relative generators here, and now I want to understand the relative generators over here. So I want to set T to be H tilde 1T of GFS I join rho bar sub. Sorry, earlier on I have a chi here, so maybe I should put a chi here as well. I apologize. Too many notations, I can't. I'm having trouble to keep track of all these conditions. Chi d and chi d dv. It's the downside of this series. Notation is a bit complicated. So now I set T to be this. Then, for any local deformation problem. dV for VET. This R rho bar frame T. This global deformation ring with fixed determinant. That's the same thing as you can tensor the local ones together. Chi V dV with T variables to generate it. And say I have S relations with S being H2. Notice this. If you note, what's happening here is that whatever I write here has nothing to do with the local condition. In the sense that somehow these generators, in fact, I can somehow take the same generator, same conditions. In the sense, I guess what we did earlier for the global deformation relative to the local deformation is universal for all possible local conditions. In fact, later on, for L not equal to P, I'll probably won't do much sort of game. But when L equals to P, at those places, I will have to choose a very small subspace inside of here. And this space will look very much different from this space. But some of the relative situations are the same. And moreover, we can use the same Taylor-Watts primes. So the Taylor-Watts primes we could choose kind of universally for all possible Ds. We don't have to change that. So that's all I'll say about these. So now, let's move to discussing what kind of local condition we see when L not equal to P. So maybe here's a next section. So local conditions, local deformation problems maybe. When L not equal to P. And then the next lecture will be the case where we discuss the case of when L equals P. So let's fix notation. My K is a finite extension of QP. And again, L not equal to P. And my Q is number of elements in the residue field of K. That's usual. Let's recall something we learned at the very beginning of this semester. The Grothendieck's L-adic monodromy theorem. You have to fix a lot of things to make the identification. So I need to fix a geometric Frobenius called Vk, and isomorphism L to L between QR bar with C, and a compatible system of root of unities. In fact, I just need L power root of unity, so L to the n of L to the n roots of unities. So we proved was that the L-adic continuous representations if you want equivalence, you want on this side to take all the Weyl representation, namely you release the action of Frobenius eigenvalue forbidden to be not. I mean, sorry. So if when we talk about L-like representation, so Galois groups, the forbidden eigenvalues must be L-like units. But if I do Wei group representation, I don't need that condition. I don't need the forbidden eigenvalues to be L-like units. If you want equivalence, you use Wei groups. But in our application, we're going to use direction this way, goes the other way. So I can read, any Galois representation will give me a Wei group representation. So this is equivalent to the following. It's called Wei delimited representation. This is the three parts over C, where R is a Wei group representation. But then this V is a C vector space. So in particular, the inertial subgroup has finite image. So R of the inertial subgroup is finite. And then N is an endomorphism ring. It's an endomorphism of this vector space V, such that if I do Frobenius on N, just think of this sort of N as a sort of time generator, but sort of linearized time, so this time. So if I have sort of the time generator here, then Frobenius inverse of that time generator of phi will be that time generator to the qth power. Now I take a log of that, I get N and 2N. Now, let's see. Okay, so how does this go? Right, so if I have a representation of the Wei group over there, I will get on this side of N being, as I said, it's going to be log of the time generator. So it will be log of rho of tau to M. For tau a time generator. And M sufficiently divisible. Sufficiently divisible so that this log makes sense. If M is sufficiently divisible, this rho tau will be an L-like units, and then I can take log. And then the action of this Frobenius times something in, so M in Z and X in inertial subgroup. So I want to describe this R in terms of the rho there. So this is equal to, well, this has coefficient QL. C. Of rho of, maybe actually this one also will be able to whole thing into C. X exponent. Basically, I have to twist this by a little. In a sense of it. So this R is roughly the same as the rho, but then I have to right multiply by the mononomial operation, where this is basically measuring how far your X, how many times X is the time generation time. So let's recall this, we discussed this equivalence before. But now, I want to introduce a notion called inertial time. Then I forget about how this delivery representation, how the Frobenius works. I only remember how it restricts to the initial subgroup. Sometimes I write this on the side for this. Okay. Restriction of the weight derivative to the initial subgroup. Just as I recall here, this image of this initial subgroup is finite. So this is a finite image representation. This is an endomorphism. This is all like sort of finite discrete data. So I'll maybe give two examples first of what these are. So let's see. Okay, I didn't write. But let's maybe go back to the earlier example I discussed at the beginning of this lecture, in the sense that if you have sort of a row universal, remember that we have this phi being 1x x1 with this 1 plus s, p plus t, of 1x inverse. Let's maybe forget about the conjugation, and then row universal of tau being of 1, 1b, 0, 1, x, y, 1. Okay? So now if I fix a point, x, in this deformation ring, the generic fiber of this. Okay? Then I get a representation rho x. There are two possibilities. Remember, we'll have two components. So possibility one, that x is on the unramified component. In that case, b equals 0. So therefore, tau is actual tau is completely trivial. In that case, the associated weight representation n is 0. And then r, if n is 0, you don't really change anything. Just basically, this r is just rho. So r is unramified. In other words, the type is sort of in this case, I say type. I mean, if r is unramified, then I residual initial group is trivial. The type I'm going to call it unramified. In the other case, if this b at x is not 0, then it is ramified. Okay? But okay, it is ramified. In this case, you can show that n is, roughly speaking, this is b. Okay, this n is it's a log of this thing. Okay, let's just maybe say bx is not 0, and then x and y are 0. This eigenvalue thing eigenvector thing doesn't really matter that much. In this case, the n is essentially a log of this matrix, and therefore your n is nothing but 0, 0, 0, e. You take log, it's basically this minus 1. Then what is r here? R is somehow, if I have some sort of a tau here, I would have to kill, I mean, this row of this tau, this exponential of this n will exactly kill the row of tau. So therefore, this r of the for me is bk. Or r is actually unramified. And r of bk is nothing but just sort of 1 plus s and the p plus t. Or I guess in this case it has to be ps, because we must be on the other component, the Steinberg component. So therefore, in this case, type consists of a trivial representation of the inertial subgroup, where n is non-trivial. So there are two different types. So one is somehow the representation is unramified. R is sort of trivial. But then n in the first case is 0, in the second case is not 0. That's sort of the picture we're trying to see here. And I hope this sort of gives you some idea of what sort of type and this deformation might look like. And now I'm going to state a big theorem. So let rho r be a representation, and I have a deformation rate. For a deformation rate, right? And for each inertial type, beside possible n, I consider the subset For this frame deformation ring, I mean, I usually write x row bar frame to be the spec of this, right? Then, if I put E here, it is that we can sort of generic fiber of this guy. So I want to look at the subspace of this one, where the corresponding representation has inertia type psi and n. I put a circ to indicate that later on this will be a locally closed subspace. When I take closure, it will be kind of closed. I'm going to describe it in terms of varieties. And I'm going to take a sort of QL bar points. So I have the universal representation going to GLN of R row bar frame, and then use X to go to a QL bar representation. So this representation at X has the inertia type. Then, first of all, each one of this is a locally closed subspace. So it's not just sort of in terms of point, but it's really locally closed subspace. Secondly, if I take the closure, its closure, say its closure is smooth and irreducible of dimension exactly n squared over E. So that was somehow the case we kind of discussed over there. In the sense that over here I didn't fix the determinant. So if I fix the determinant, this will be of dimension n squared minus 1 over E. So that was this is somehow the generalization of the two-dimensional case we just computed. In the sense there are two components in that case. Each component is labeled by an inertia type. So what we're saying here is that in general, the irreducible component of this guy is labeled by inertia types. Of course, for some inertia type, there's no such inertia type appearing here. The corresponding component is empty. But all the components, each component has a specific inertia type. And all the components are actually smooth and irreducible. So, as I said, we're not going to prove this. And maybe as a corollary of this, essentially, we're saying that the Crew dimension of R row bar frame is n squared plus 1. Remember that when we use this Galois-Coulomb calculation to show that this Crew dimension is at most n squared plus 1. But now you see the generic fiber are very nice, and they are actually smooth. And the smooth is very strong on the generic fiber. And that particular says that the Crew dimension is precisely n squared plus 1. And in fact, people can show that all the irreducible components, so this deformation ring is of pure Crew dimension n squared plus 1. And their generic fibers are really smooth, dimension n squared. But of course, the special fiber will be very bad. They have lots of bad singularities at a special fiber. This will be important for us later on in the sense of when we compute the global dimension of the global deformation ring. This is important to know that the local deformation ring is a pure dimension of certain thing. I think that just give us some sort of information of this. Okay, so I'm not going to prove this big theorem, but I want to give you some indication why it's natural to expect such a theorem to hold. So let's consider an E point. My coefficient is E, where E is over, if you remember last time. My setup is E is finite over QL, and O, and somehow the random integer is O, and the uniform either is this. Okay, this is F. That was my setup. So consider an E point X of this deformation ring. Of course, I can, if I want, I can enlarge my E to a bigger finite extension. So therefore, essentially, I enlist all possible QL bar points of this deformation ring. So let's maybe fix one field of definition and discuss that. So I have an E point of this. Then I have a continuous representation coming from the universal one. So I start with the universal one. And I do X star maybe go to GLN. So this is a continuous representation that lifts the row bar. Maybe let me say first. So this will first go to OE because an E point will map first. This will first map to OE, and then this is contained in GLN. Okay. Let me also point out that this X is actually a point, so therefore, this X star of this maximal ideal is contained in the maximal ideal, or rather, the var power. So row X is continuous. It's a continuous representation. Okay. So now, instead of deforming the residual row bar, I can deform this row X. So to set it up, let me maybe write this complete Noetherian local E algebra. This is all the complete Noetherian local E algebra A, such that the structural map from E goes to A, modulo maximum ideal, is an isometric. So I consider the following deformation problem. Now I want to deform this catch reduced to 0 coefficient representation. It sends A to O the representation rho from K goes to GL and A such that rho modulo maximum ideal of A is my rho X. So consider this local deformation rate. This deformation of rho X. I want to say that this deformation of rho X will tell me the universal deformation for the residual elementary row bar if I complete at this point X. So that's how I know the structure of this universal deformation space at each of the places at the generic points. So theorem. The completion on my frame converging L completion for R row bar frame M and the maximal ideal determined by X. So this completion represents the functor of rho X, right? That's fine. It's a proof. So we need to prove a bijection. Basically, what I mean by this represent set, so basically I need a bijection from Hom of CNLE of R row bar frame. Bijection means that whenever you have a ring A, somehow all the possible deformations to this ring A comes from, it's the same thing as a Hom from this whatever ring represents the function to A, right? So I need to show that this is equal to all the lifts. Continuous, of course. And this is the right continuous side. I like the lifting. Okay? So I need to show this. So then, like, I guess given the homomorphism, I want to construct a representation and then vice versa. So let's do it more carefully. So let's go this way. So first, given the homomorphism, continuous, I guess it's still continuous. Given a homomorphism from our robot frame X to A. By how I define things, we define things. This will mapping basically the maximum ideal at X to the maximum ideal of A. It's part of the sort of definition. So therefore, this is I guess because of this is a continuous thing. And now, it's very easy to construct a representation because, just rho, just compose with the universal representation. So GLA of R rho bar frame. And goes to, of course, this process completion and then compose with this map here. So this gives you a continuous representation. So this is good. This direction is sort of trivial. But now let's go the other way. So the other way takes me. So conversely. Given a rho, let's just say, given a representation, so. Okay. I can first of all compose it down to quotient out by the maximum ideal to the R power if I want. I'm going to call it rho R. So I'll work with this A mod maximum ideal of A to the R power, work with this for each R. And then I will kind of patch together. So I want to define, the idea is that I want to relate this to the integral version. So I have to define something a little bit smaller. Let me call this one AR. It's A quotient by its maximum ideal to the R power. So I want to define the integral version of this. So this is an O algebra generated by entries of rho R of gamma for gamma. Okay. But then I note that AR is, well, remember that my A is a complete Noetherian local E algebra. And then quotient on maximum ideal to some power, so this becomes an Artin E algebra. And therefore this is a finite dimensional over E. And on the other hand, the Galois group is compact. These two together will show that this AR circ is actually a finite O module. Because if GK is compact, the A sub-algebra generated by O must also be compact. On the other hand, this is a finite vector space, so therefore every compact O module must be finite. So this is a finite O module. Let's see. I'm going to draw a diagram. Let's move up. So now I want to consider the representation of this go to GLN of AR circ. And this one, if I quotient out by AR circ modulo the maximum ideal of A intersect with AR circ. Okay? What do I get? Well, first of all, such quotient must embed into GLN of A, what is the maximum ideal. But this is E. Right? But on the other hand, my AR is a finite generated O module. It's a finite generated O module inside of E. So therefore, this can only be just O. If I quotient by this, it must be O. And therefore this, I guess, okay, if I quotient further by modulo the uniform either, I will just simply get F. Okay? And on the other hand, if I go from this modulo maximum ideal, or maybe I can sort of go further down to GLN of AR. Right? And over here, this is mod maximum ideal. So if I go this way, I will get rho R here. If I mod maximum ideal, because it lifts the rho x, so this is rho x. And we know that rho x, in the sense that rho x has image in GLN O, so this must be sort of, I guess, integral version of the rho x. And the modulo pi, because my x is a point in the deformation ring, so therefore this rho x modulo, or like integral version of rho x modulo modulo uniform either, this must be rho 1. Thus we know that this therefore we see that this rho R circ is a representation after modulo maximum ideals, it becomes the rho bar. So therefore it lifts rho bar. So by universal property of deformations, I get a natural map from rho bar frame, R rho bar frame to AR. Okay? And then of course I can invert L on both sides now. So then I get R rho bar frame of L mapping to circ inverting L. This of course maps further to AR because it's a subring of R. Now on the other hand, because the representation, if we get to the R side, residually factors through the ideal. I guess somehow. I guess if you quotient out by the maximum ideal of OR, you get to E, and this is the usual X star. Right? So therefore, you know that this map, this composition, must send the maximum ideal in X to maximum ideal in A, and therefore I can complete with respect to on this side, and then I get completion on this side, which is the same thing, which itself is already completed. So therefore I get a ring homomorphism from this completed at X going to AR. And this argument works for all R. And then I take inverse limit. Then I get a moves from the completion of the general fiber of the general fiber of the deformation ring at X mapping to A. Okay, so that's how to go backwards. With a little bit of twist that you can't work with A itself, but rather each time you're truncated by some power maximum idea to make things more finite. So what does this tell you? It's a corollary of this. Is that a point X in the spectrum an E point of this is a smooth point. If you want to know whether this point is a smooth point of this deformation ring, is equivalent to saying whether the completion at this point is a power series ring. But then we have this so that power series also represents this deformation problem. We talk about how this sort of deformation problem, whether in which case is such thing as a power series ring. At least in the case when the H2 is 0. Here's not rho bar anymore. Now this is rho x. At least when the H2 of this is 0, this completion of the general fiber at X is a full power series ring, and therefore it's smooth as point. So now with this at hand, let's maybe do an example to see which point of the general fiber of the deformation ring is smooth or not. So here's some example of why somehow I'm claiming that the general fiber of this local deformation ring tend to be smooth. At least irreducible components are smooth. Or at least maybe I won't be able to explain that much. I'll probably only explain like generically it's going to be smooth or nice. Or sort of lots of points are going to be nice. And maybe you can have some sense of the bad places. So say my rho bar, just for simplicity, is iramified. And then my phi k will be mapped to, say, a diagonal matrix. Let's say that all the alpha i's are different. Okay? So I can talk about, for example, an unramified point, an unramified lift. Lift of rho bar to E coefficients. Unramified lifts basically you have to lift the rho bar. Let me call it rho x. Okay? So this is up to conjugation. So conjugation really doesn't matter. So let's forget about it. Let's say up to conjugation, this is just alpha 1. Alpha I. So alpha I lifts alpha I bar. So when is this a smooth point in the deformation ring? It's not always, of course. It's not always a smooth point. Well, let's see what kind of conditions make it smooth. By corollary, I need to know when H2 is 0. Okay. Well, it's not very useful. This condition is bad. But I want to say this is equivalent to an easier to use condition. This condition is equivalent to the H0 by local technology. much easier to check condition. Okay, so let's see. Let's check that. So what are the forbidden eigenvalues? Let's see, eigenvalues are, let's see, right, so rho will have eigenvalue alpha 1 through alpha n, but dual will have eigenvalues alpha 1 inverse to alpha n inverse. So if I take them together, you will have alpha I over alpha j. Okay, alpha I, alpha j inverse. But after that, you have a twist by 1. So q inverse. Okay. So basically, the invariance of this is non-zero if and only if some pair alpha I mod alpha j equals to q. So of course this only happens if residually two pairs alpha I and alpha j, the ratio for them is q. Okay? And such point is typically not a smooth point on the deformation space. And in fact, if we consider, remember the earlier condition that whenever there's the deformation, there's two forbidden eigenvalues, 1 and p, or p is same as q, right? Whenever two forbidden eigenvalues, the ratio is p. There's always a Steinberg component through that point. So, and in this case, there's a Steinberg component through X. In the sense that we showed that for this unrelated deformation, somehow for most of the points, of course for unrelated deformation you can probably see immediately it's a sort of smooth component. But I'm just using this as an example to explain the general situation, where somehow for most of the points you can show on the node set that this invariance is 0, then it's smooth point. For the point where it's not smooth, usually the condition corresponds to some sort of alpha I over alpha j being a power of p. And the reason that point is not smooth is because we know there's another Steinberg component through that point. And that's causing it not smooth. But it's not because this irreducible component is not smooth, but somehow it's because the intersection of two smooth component, and that's lies in the intersection. So that's usually the situation. Maybe let's look at another situation in a Steinberg component. Let's say, just for the interest of sort of working out more examples. So suppose that I have three eigenvalues. Their ratio is 1, qv, and qv squared, modulo bar pi e. And take a Steinberg lift. And I'll consider a Steinberg lift list. Namely, I want to consider the case rho f is some alpha 1 and truly alpha so q alpha 1 and q square alpha 1. And then rho x is in tau k. Of the time generator is 1, 1, 1, A, B, C. I don't know. Let's say A is not 0 and C is not 0. Okay? But suppose that we're in such a situation. Then maybe we'll count the simplest. Maybe we'll count a simpler example. Just for simplicity, let's say we take an example where this is 1, 1, 1. Hold on. This is somehow the typical example. And I want to ask another question. So this is a typical point in Steinberg lift, where the forbidden eigenvalues have a ratio of 1q and q squared, and the Steinberg is sort of a full Steinberg. And maybe let's ask if this is a smooth point or not. Or equivalently, I want to understand what is rho x 1 of gamma k. I want to rather that's 0 or not. Okay, so let's do a computation. So let's see. So this is a representation of rho, right? So let's make another representation. Let me call it R. It's a two-dimensional representation. Gamma equals QP. So it's GL2. It sends phi k to 1 and q, and then tau k to 1, 1, 0, 1. And if, in fact, you see that this particular case, rho x actually is a symmetric power of Rx. Okay. Basically, if it doesn't work, I'll change some variables to make it work. So let's see. So what are the bases for the symmetric power? The bases are E1 tensor E1, E1 tensor E2 plus E2 tensor E1, and then E2 tensor E2. Okay? So, right. Let's see. Maybe make it this a half. Okay? So what is let's maybe so what's the phi action? The phi action is that phi on E1 is E1 and phi on E2 is Q. Right? So therefore, phi on this one has eigenvalue 1, and on this one has eigenvalue Q, and on this one has eigenvalue Q squared. So that's basically what I have over here. Or maybe I'll just might as well just write R for 1 being 1. Because it's just optocentric, so it doesn't really matter. And then what about tau? So tau will send E1 to E1 via this, and then tau of E2 will be E1 plus E2. Let's look at the picture here. So tau will fix E1 tensor E1, and tau will send this one to, I guess, itself, plus replacing this E2 by E1, replacing this E2 by E1. So therefore, these two add up together to get this thing. So therefore, you have this second column here, 1, 1. Okay, the third one is the tau E2 tensor E2, equal to tau E2 tensor E2. Right, that's sort of E1 plus E2. Tensor was E1 plus E2. Okay? And that's the same thing as E1 tensor E1 plus E2 tensor E2 plus E1 tensor E2 plus E2 tensor E1. Okay, this is quite the way I want it to look like. Let me just replace it by 2. So that it's equal to symmetric power. I mean, generally you can adjust the norm of E1 and E2 so that somehow all these sort of general ABCs are essentially of the form, as long as somehow these two numbers are not 0, are essentially form of symmetric power, something like this. So I'm going to draw on that. So just assume that my rho x is symmetric Rx. And now what is sort of an adjoint representation of rho x? So this is sort of a representation theory for SL2, or GL2, right? So I can write this 3-way spaces. And so if I do adjoint, it means that it's symmetric power tensor with symmetric power dual. So I will do this and this. If you know what I'm doing for representation GL2. So if I look at this, so I will have this representation and this representation and this representation. So interpreting that will be symmetric fourth power of Rx tensor with det minus 2 direct sum with sigma this guy 2 tensor with det minus 1, and then direct sum with the trivial representation. So maybe now let's twist by 1 everywhere. So now this becomes E1. Okay. So that's what adjoint representation of the symmetric square. Yes. So now let's look at the forbidden eigenvalues. So what are the forbidden eigenvalues here? Forbidden eigenvalues on this one is just Q. Just Q inverse. I'm taking the geometric And what about this one? This one's a symmetric square. Okay, let's maybe look at an example here. So symmetric square is 1q and q squared. But then I have to take the determinant inverse. The determinant is q, and I take inverse of that. So now this 1q, q squared becomes q inverse 1 and q. And then twist by 1. So I further multiply by q inverse. So I have 3 eigenvalues here. Q inverse these 3. Basically dividing this matrix by q squared. 1 from the determinant, 1 from the twist. Now symmetric fourth power. Symmetric fourth power, so this one will have 1q, q squared, q squared, and q fourth. And the determinant minus 2 and 1 will be multiplying everything by q to the negative 3 power. So therefore I have q minus 3, q minus 2, q minus 1, 1 and q. Okay, those are the for these eigenvalues, where eigenvectors are kind of clear. But now what about the inertia invariance? Inertia invariance, which one is invariant and inertia? The inertia invariance is always sort of the highest weight. Which one are highest weights? Those are precisely the leading ones. Those are the somehow inertia. Invariant subspaces. But unfortunately, none of these is invariant under the forbidden section. The forbidden argument is not 1. So, this invariant algebra representation, taking invariant subspace under the gamma group, and therefore this point here is a smooth point on this sort of Steinberg component. So in general, what people can do is work out the combinatorics of how these components intersect. And I guess if you use fancy language, you can do sort of local models of these things. They basically, on the GR fiber, they intersect transversely, mostly. And that's sort of the basic idea.